Darling West Lecture Theatre. This is where I did first year physics in this lecture theatre. As a student. So, has anyone tried this? It's not there. Has anyone tried this? What'd you get? Oh, look at it. Tell me about this. Well, maybe someone else could tell me about this. Why are these linearly dependent?
They're linearly dependent because...
I'm going to get someone else to. Is that okay?
Yeah.
Could someone else explain why these are linearly dependent? It's okay to not know. Stick him in a matrix and you can get the identity, you tell me. Okay. All right. What does someone else have to say about that? I will start the proper revision seminar shortly. I just was interested to see what people would do with this. Yep. You can make one of them as a combination of the other. So this one is that one is 2 times that one. So that means they have to be linearly dependent. You're telling me. Okay. So if one of them is a multiple of the other, they'll be linearly dependent. Cool. All right, I have another one for you to try. And you don't have to do it individually. Now try. Feel free to talk. Cute. All right, I'm going to let you ponder that for a while we discuss what I'm going to talk about today. So, I've had many and varied requests, and I probably can't fit them all in. So, I've had someone just this morning send me an email about covering various integration questions in a past exam. So essentially trying to choose what integration method you're going to use when faced with random integrations. Also I've had another one about having a plan of attack for reduction formulas, so sort of strategies that you might be able to use when you're trying to make a reduction formula. I've had various requests about optimization, and I've had various requests about subspaces and basis and linear dependence, which is one of the reasons I made this, so that we could play around with linear dependence for a bit. So, how are people feeling about what you would like me to talk about? We can add extra things to the list, which will make the choice harder, or you can confirm one of those things. Feel free to sing it out. Reduction formulas sound good. They're one of the longest bits of integration, especially relative to the amount of time was spent on it. So, how do other people feel about me talking about integration sorts of things? We've got some various nods. Okay. But I might talk a little bit about linear dependence before I get onto that, since that's what's on the screen. I'm not expecting anyone to come up with something quickly. It took me a while to even tell if this was possible. But I would like maybe some people to give me some thoughts on whether this is going to be linearly dependent in the same way that the first example was. We've got a shake. Why is that?
Well, if you're assuming those are the only two negatives, you can have them, you can't multiply by any constant to get the right number of negatives, so it has to be a sum. Like one vector is the sum by some multiple.
I really should have brought the microphone up because now I have to repeat all of that. So you're saying that if I'm only allowed to use positive numbers in all the other boxes, and these are the only two minuses, I'm not going to be able to make this one as a multiple of that one, because either it would have to have the minus there, or both of these would have to be minus, and this one can't be a multiple of that one, and this can't be a multiple of either of those. Okay, so one of the morals there is it is in fact possible to be linearly dependent even though none of them are multiples of any of other single ones. And so you were saying you'd have to be maybe adding some stuff. Or subtracting. Okay. So you could be attempting to add or subtract, maybe add these two together to get that one. All right. It's really interesting to think about what the possibilities are for doing that with the numbers from 1 to 9. It's not actually that. You can't make this third one by just adding those two.
Could the third one be a scalar multiple of the first two added?
That's okay for it to be, yes, a scalar multiple of the first two added, so something like add them together and then like divide it by 2 or something.
Yeah.
I haven't tried that. Maybe it'll work. In fact, it could be the other way around. It could be the middle one that's like the first one and the last one added and then divided by 2 or something. All right, so there's all these possibilities. There's so many things you could try. Very interested if someone comes back to me with an answer because it's different to the one that I came up with. That would be exciting. Anyway, so what we've done is we've thought about what possibilities are, and one of the morals I wanted to make from doing these two puzzles is that you can do any combination you like. You know, it could be 2 of the first one and a third of the second one equals the next one or something like that. As long as some combination of some of them produces one of the others, then they're guaranteed to be dependent. Someone said something about row reducing to get the identity. So if they were dependent and I put them in a matrix and I did the row operations, would I get the identity or would I not get the identity? I'll get a row of zeros if they're dependent. So that won't be the identity. I'm just going to ask you something. Okay. Do you have to get a row of zeros if they're dependent? I mean, with these vectors, yes, you do. What if the vectors were more like those 3 columns, that one, and that one? Are they linearly dependent or not? Yes. Why are they? Well, sorry. Are they linearly dependent?
They're dependent.
And how do you know?
Because there are more vectors than variables.
So in case you didn't hear that, and definitely the people who are listening online can't hear that, there are more vectors than variables. So if you have more vectors than there are coordinates in each vector, then they have to be dependent. So what happens when you do the reduced row echelon form of this matrix? Let's see. This minus 2 of that would be 0. And this minus 2 of that would be 0. Okay, so I get this. I think I've done all my operations right. If I was doing this properly, I should really have written down what row operations I did. It's minus row 2. Row 1 is row 1 minus 2 of row 3. Okay. So I know they're linearly dependent, but I didn't get a row of zeros. Why didn't I get a row of zeros?
Is this not a pivot on one of the columns?
Okay. So you're saying I know they're dependent because there isn't a pivot in this column? Is that what you meant?
Yeah.
If this had been longer and they were dependent, then I would totally have had a row of zeros. It's just these vectors aren't long enough. They don't have enough coordinates to produce that row of zeros. So one thing that's really important to realize is that you can look for rows of zeros, but only if your matrix is long enough. And you've hit the nail on the head there. The important thing to look for is where the pivots are. I've found pivots in every column. Not every column. I've found pivots in these columns, and it's going to be impossible to produce a pivot in this column because I've already used up my identity matrix columns. So I get there's no pivot in this third column, which means they must be linearly dependent. So it's much more productive and safe to look for pivots than it is to look for rows of zeros. And I should also say that what with your, you're not being able to take a device that will do reduced row echelon form for you into the exam, it would be useful to be able to shortcut this process a little. You can tell they're linearly dependent back here because of this staircase here. There's going to be a pivot here. Oh, there's already a pivot there, and there's going to be a pivot here, and it's going to be impossible to produce another pivot, and so you can tell from this one that they are linearly dependent. Of course, to be fair, we could tell right from the beginning that they were linearly dependent because there were too many of them. So one of the morals of this tale is it's better to have more than one way of figuring things out because one of the ways might be shorter today. You don't have the luxury in a 2-hour exam. It is 2 hours, isn't it? Okay, they keep changing it, so I just kind of need to keep track. If you look at some of the old revision seminars, back in those days, it might have been 3-hour exams. They switched them since I've been doing these. So you don't have the luxury in a 2 or even a 3-hour exam of always doing it the same way, even if it takes longer. Now, to be honest, if you only know one way and you know it really well, then it's best to use that than nothing. It's good to know alternative ways, and it's one of the reasons you've been given a list of different things that tells you whether things are linearly dependent or not. I might as well finish off the list while I'm at it. Okay. So these are not in any particular order. Only one of them is a definition. So I'm just going to say some random things. We've already seen 2 things. One of them is a multiple of the other. That will make them linearly dependent. Doesn't matter which ones they are. And it doesn't matter if there's 15 of them and just this one's a multiple of another one. They're linearly dependent as a group. One is a linear combination of some others. That makes them dependent. So we already covered that one. It could be that this one is like 2 of that one and 3 of that one, or it could be that you add them together and divide by 2. Yep.
Does it have to be the entire group made into... Never mind.
And the answer is no, it doesn't have to be the whole group. If any one of them is a combination of any others, and you don't have to use all of them at once, it'll automatically be linearly dependent. And the reason is, and you've just set it, all the other coefficients are 0, and so technically it is a combination of all of them, because you could just put 0 in front of the ones you haven't used. Okay? Even better than this, you only need one of them to be a linear combination of the ones before it in the list in order to be linearly dependent. So I'm just going to do that backwards. If when you look at them, and you start from the left or the right, doesn't matter, and you say this one's not a linear combination of the one before it, and this one's not a linear combination of the two before it, and this one's not a linear combination of the three before it, and you go all the way to the end, then it's guaranteed to be linearly independent. So you can say none is a linear combo of those before it. Independent. This is a really good one, because if you thought that this was the definition of dependent, then you would have to check if every one of them was a linear combination of any of the others. But actually you only have to check the ones before it in the list, which makes it really nice. So you can say, for example, that one, you can say straight up that they are linearly independent by working your way through it. You can say that this one is not a linear combination of that one, because if it was, there would be a 0 in the middle. And this one's not a linear combination of those two, because if it was, this would have to be a 9. Because it's already that's the sum of the first two, and that's the sum of the first two, and that one isn't the sum of the other two. Now, I don't know if the person marking your exam will be okay with that, that last little move, but it's a good one to check for yourself. Traditionally, it's easier when there's lots of zeros. We'll just leave that one there. 5, 7, 6, not a multiple of 103. 6, 7, 8. I can say that 6, 7, 9 is 103 plus 5, 7, 6. And this is not a multiple of either of these away from that answer, the one that we've got. And so I can go that so I can say that this is a linear combination of those two, and this isn't, and so therefore this can't be either. Because it's a combination of something that is a combo of the others and something that isn't. So there you go. Not good. I don't like this, sorry. This is the problem where when I make things from scratch. That one we definitely can do. We just do it in reverse. 0, 0, 5. So, damn it. 2, 0, 0. Right. Not a combination of 0, 0, 5. And 1, 10, 3 is not a combination of 2, 0, 0. And 0, 0, 5, because if it was, the middle position would have to be 0. And so therefore they're linearly independent. It's a particularly nice one, that one. It doesn't matter what order they're in, as long as you can slowly build them up and say this one's not a combination of those two, this one's not a combination of those three, and keep going, it'll be good. Of course, you can always stick them in a matrix and row reduce, which is an option. With vectors as columns. Important to put them in as columns, even if they're written as rows. If you put them in as rows, there is a way to do it, but we're not up to that yet. It's that in Maths 1B. So, row reduce the matrix with the vectors as columns, and if you get, just a second, we just covered that. Pivot in every column. Implies independent. And any column has no pivot. Implies dependent. That's the surefire way of knowing. And, oh, there's one more. Yep.
What happens if you get no solutions?
Sorry?
No solutions?
Ah, well, you said no solutions. There isn't an answers column in this thing, and so you don't get no solutions. In fact, technically, your answers column is 0, 0, 0, however many zeros, because of the definition, which I will write down. Definition, you do x, k, vk equals 0, has more than a unique solution, implies independent, and any other solution implies linearly dependent. That's the definition. And that's what you would need to use if you were doing a proof. And so the idea is that when you put vectors in as columns, what you're doing is solving this equation and figuring out what the x's are that go with it. And technically that 0 vector means that even though you haven't written it down, there's an answers column on the end which is 0, 0, 0, 0. And so that's why there's always a solution, because you never get that thing happening where you get a row of zeros equals 1 or something. So that doesn't actually happen, so you don't have to worry about that. And the final one that you can always use is that one of the vectors is the 0 vector, and that will make it dependent. Always. And that's because the 0 vector is a linear combination of anything you like. It's 0 of anything. And so, yay. But even just the 0 vector all by itself is linearly dependent. Okay, so e.g. Yeah, 0 vector all by itself is linearly dependent. And that's important. And it's because when I do x times the 0 vector equals 0 vector, I can choose the x to be whatever I want. So there's more than one solution. So, yeah. Okay, they're all the ways to tell if things are linearly dependent or not. And so if you're asked, are these vectors linearly dependent, it's not the worst thing to have a quick look to see if you can tell if one of them is a combination of the others before you try anything else. Okay, beautiful. So before I move on from this, in subspaces, the 0 vector all by itself, just like this, is a subspace. And to make a basis for a subspace, you need a set of vectors that spans it, and the 0 vector certainly spans the 0 vector. Every vector spans itself. But you need a set of vectors that's linearly independent as well. So the only vector that spans the 0 vector is the 0 vector, and the 0 vector by itself is linearly dependent. So the 0 subspace has no basis. The 0 subspace has no basis because the only thing that spans it is linearly dependent. And that's why the 0 subspace has dimension 0, because the number of vectors in its basis is none. There are no vectors in its basis because it doesn't have a basis. So, just so you know. Therefore, the zero subspace has no basis, which means dimension 0. That's not the right closing bracket. Right. Therefore, dimension 0. Just worth pointing out, a lot of people who are new to this area, as you are, will usually say that the 0 subspace has dimension 1 because it's got a vector in it. But that's not true. It has dimension 0 because it doesn't have a basis at all. Yay. Okay. So, all right, and that's good. And then everyone was okay with me talking, well, a lot of people were okay with me talking about integration, and so therefore I will talk about integration. Now, I'm not going to do my fabulous integration revision seminar that covers all of integration, because that takes about 3 hours to do properly. And there's all sorts of integration stuff on the website already. What I'm going to do is cover particular questions that people are interested in since you're here. Right, let's see if I can find the thing I want. Okay. And do some miscellaneous integration. Now, I really like doing integration because I've figured it out. So I've been doing Maths Learning Centre for 9 years. So after 9 years of Maths Learning Centre, of doing Maths 1A twice a year, I've figured it out. Okay, so I really enjoy doing integration. But one of the things that helps me enjoy doing integration is the fact that I have a list of things that I like to try. Oh, come on. This is my list of things that I like to try when I'm doing integration. There are technically 8 things on that list, and this handout is on the Maths Learning Centre website. Whenever you have a thing you need to do which is complicated and has a large number of different things that you could try, it's a good idea to put them in an order that is more likely for the earlier things on the list to work than the later things. And we sort of try the simpler things before the more complicated things. So you'll see that reduction formulas, which are actually the hardest of all of these, are number 4 on the list, and trig substitution, which takes forever, is number 5 on the list, and partial fractions, they're actually not that bad, but still they're quite complicated, are number 6. And do it numerically is actually giving up and going, no, can't be bothered, I'm just going to do it numerically. Well, actually, sometimes it's not possible to integrate because you don't have a formula for the function, you just have some of its numbers. So anyway, so these ones on this side over here are the harder ones that just take longer. And so anytime you want to try something, you should try one of these first. So the first thing on the list, well, technique 0, which doesn't count as a technique, is just do it because you already know the answer. It's like x cubed, I'll put the power up by 1, divide by the new power. Done, okay? You don't have to do anything fancy, you just do it. Technique number 1 is rewriting it. Expand some brackets or factorize it or use a trig identity, which sometimes takes a while, but sometimes it's pretty fast. So rewriting what's inside the integral there, you're not really doing anything other than algebra. That's the first thing you should attempt to do. And then after that, there are 2 fundamental techniques of integration, which are substitution, which is designed for when one part is close to the derivative of another bit, or in general when there's something inside something else. And then by parts, which is for things that are multiplied together, and it's like the product rule for integration. Like differentiation as product rule. And all the other ones are special. And I've lined them up next to each other to see what goes together. So partial fractions is just a very fancy way of rewriting things. You're not actually doing anything to the integral other than rewriting what's there. And trig substitution is just a very fancy kind of substitution, which is why it's next to substitution. And reduction formula, not always, but usually, is a very fancy way of doing a whole lot of by parts all at once. And so I've lined them up like that because they go together. So that's my way of organising the techniques of integration section of your course, which, when you look at all the stuff that's in it, you would think, when looking back on it in time, that it took you like 6 weeks to do. But it didn't. Right? It was only, what, 3-4 weeks of techniques of integration? Maybe not very long at all. It feels like it was 6 or 10 weeks because there's so much stuff in it. So a lot of people every semester are worried about integration because there's a whole lot of different bits in it and they don't necessarily know all the bits. There you go, that's the beginning of that. So I'm going to use this strategy to deal with various integrals. I've been given a list of ones to try, so I'm going to try them and we'll see how we go. Go back to the document camera. Okay, let's do this one. So on my list of things to do, the first thing to do is to just do it. Now it doesn't look likely. If that wasn't there, then I could have rewritten it. And I could rewrite that as minus 4x to the minus 2, and now it's a power, and I can put the power up by 1 and divide by the new power. But I can't, because that 4 is trapped there. Could I maybe expand some brackets? Yeah, minus doesn't interact with division that way. You know, if the 4 minus x squared was on the top, I'd be good. I could divide each bit by 4, but division doesn't behave that way, so no, can't do that. What's next on the list? Substitution. All right, well, usually in substitution you find the most annoying bit and you call it u, and like this being on the bottom is annoying, so we'll call that u. But we'd need the derivative of that to be there, which means we'd need like an x on the top, because the derivative of that has got an x in it. And we don't have that x on the top. So substitution's not going to work. So substitution's not going to happen. By parts, yeah, it's too hard. I could probably do that by parts. Well, I'd need to pick some... write it as two things multiplied together and integrate one and differentiate the other. Now, I don't know how to integrate this, so I could do 4 times 1 on 4 minus x squared, but I don't know how to integrate that. So I'd have to differentiate it, which would turn to crap, right, because of the quotient rule would make it go up to 4 minus x squared squared. Yeah, it's just going to be insane. So no, so by parts is not the go. Oh, so I'm going to have to use one of these other ones on the other side. Well, partial fractions is specifically designed to deal with things that have polynomials on the top and or the bottom. And that's what I've got. So partial fractions is what we're going to do. Trig substitution, I could do a trig substitution, but that partial fractions is actually easier. So let's see. I'm going to have to factorise the bottom. All right, they're both squares, so I can do this. I can do that. Bottom is factorised. Okay, so now that the bottom's factorised, I can rewrite the thing in there like this. And I can attempt to separate those two pieces into their own fractions. So there's going to be something on 2 minus x and something on 2 plus x. I don't know what they are, but the theory of partial fractions tells me that there should be a single number a and a single number b that will allow me to do this. Sorry? Oh, well, just give me a second and I'll get there. The idea is that if I rewrite this with the common denominator, it should match the 4. So if I take this one and I multiply it on the top and the bottom by 2 plus x, then it'll match the denominator of that one. And if I take this one and I multiply it on the top and bottom by 2 minus x, this is the long version, you can skip some of these steps, then they'll have the same denominator and I can add them together. Yay, okay. So, these two things here, that one and that one, are supposed to be the same thing, which means that this top is supposed to work out to 4. So I have multiple choices for how we're going to deal with that. One is to expand it out and make them into a polynomial and match up the coefficients. And one is to sub some things in for x to figure out, and sub some things in for x, and that'll give us some equations to solve to figure out what a and b are. Technically, if I sub in x equals 2, that'll make a 0 here and the b would disappear. But x equals 2 doesn't actually work in my original formula because it'll put 0 on the bottom of the denominator. But there's some technical limits stuff that tells me that it works anyway, so I can do that if I want to. So one thing that some people do is they do this. When x equals 2, I get a times 4 plus b times 0 equals 4. 4a equals 4 and a equals 1, therefore. And when x is equal to minus 2, I get a times 0 plus b times 2 minus minus 2 is 4. And so b times 4 divided by 4 is 1. And so I can figure out what the a and the b are. Alternatively, you could do it this way. Or I could expand this out. 2a plus ax plus 2b minus bx equals 4. So that's 2a plus 2b plus a minus b lots of x equals 4. So I've grouped together the constant terms and the x terms. And because this is a polynomial and this is a polynomial, and the only way that polynomials can be equal is if their coefficients match, this one doesn't have an x. And so I get that 2a plus 2b equals 4, which means that a plus b equals 1, and a minus b equals 0, which means that a is equal to b. And if a is equal to b, I can sub that in there. That should totally be a 2. Well done. And if a is equal to b, I can sub that in there and get 2a equals 2, because a plus b, which is equal to a. And so a is equal to 1, and therefore b is equal to 1. So that's two different approaches to doing the same thing. Choose whichever one you think is best. Up to you. This one is ever so slightly dodgy, but there's some technicalities that mean it's okay after all. And this one is completely kosher. So, yeah. This is the one that you'll be likely to be using if you ever do auto control in the mechanical engineering degree. And to be fair, you may never use it again if you're not doing mechanical engineering. Except if you're doing Maths 1B and you have to do logistic formula. Okay, so once we've got that, therefore, my integral is equal to 1 on 2 minus x and 1 on 2 plus x. The whole purpose of this was to figure out a way of rewriting that thing in terms of two fractions that I know how to integrate. All right. So let's have a look. I know how to integrate them because they are, well, if this was just an x, the integral of 1 over x would be ln x. Well, with an absolute value. And it's not an x, but the thing that is there, its derivative is a constant. So all I need to do is divide by that constant as I go, and it'll work out just fine. So this will be ln of the absolute value of 2 minus x, but I have to divide by the constant here, and I'll get that. And this one, if that was just an x, I would do ln, but the derivative of this thing is a constant, and so I'll divide by that constant. Technically it's substitution, but you're allowed to put it in the just do it category because it's so common that you can just do it. And so I get minus ln of 2 minus x plus ln of 2 plus x. With a big plus c because it was an indefinite integral. So just to let you know, if this had been a 2 plus 3x, I would have put a 1 on 3 here, because it's the constant derivative. How do people feel about this? All right. I should say, if you wanted to, you could go further than this and use your log laws to simplify this into a single ln of thing divided by thing. But it's not really necessary. Not for this problem anyway. Okay? Let's do our next one. Cos 10x, cos 9x. All right. Well, let's run down our list. Just do it. Well, if it was just the cos 10x, I could just do it. The integral of cos is sine. The thing inside there has a constant derivative, so I just have to divide by that. So I'll get 1 over 10 sine 10x if it was just that. And if it was just this, I could do it as well, but I can't because they're multiplied by each other. Okay, so, right, so I could rewrite it. Well, it's trig-ish, so there's probably some sort of trig identity that I can use to rewrite that as something else. Let's do that. I might have to make my own trig identity. Okay. I know that if I'm going to think backwards here, I want to imagine a trig identity that I know that has cos something times cos something. And the trig identity I know that does that is this one. The one for adding trig things, adding things inside the cos. And that will put the cosines together. Because, of course, cos and sine have this one-sided love-hate relationship. Sine likes cos, and so when you do sine of a plus alpha plus beta, the sines and the coses end up together, whereas cos doesn't like sine, and so when you put the coses, when you do cos of alpha plus beta, the coses are together and the sines are separated from them by a minus. That's a really bad reason, but it's the one that I know. It's the one I remember. So that's nice. This would be good. If the alpha was 10x and the beta was 9x, that'd work. But I do have this other bit, annoying bit here that I don't have. Just a second. If I did it with a minus, then there'd be a plus here, and then if I added these together, the sign bits would disappear. That's cool. Okay. So it looks like I get that cos of alpha plus beta plus cos of alpha minus beta is 2 lots of cos alpha cos beta. And that's really very close to what I have here. Except for the 2, I'll just have to divide by that. So let's see. Cos of alpha. Damn it. Sweet. So therefore, what have we got? The integral of cos of 10x cos of 9x dx will be half of cos of 19x plus half of cos of 10x minus 9x, which is just x. And those I can do. The half is multiplied on, so it will still be there afterwards. The integral of the thing inside here, the derivative is a constant, so I can just pretend it's an x, which would mean that cos will go up to sine, but I'll have to divide by the constant derivative. The half is multiplied on, so it's still there. Cos goes up to sine x. What, 38? Bang! I made my own trig identity. To be fair, if you go and look up a list of trig identities, that one will be there. But I can't remember that one. And in the exam that I'm getting this from, it said, hint, use the identities cos A plus or minus B equals blah, blah, blah. But I didn't reveal that to you because I wanted to run through all the other possibilities. I would like to do this a different way. Not that you would do this in an exam, that would be a whole waste of time, but I think it's illustrative to do this another way. Or, let's do it this way. Ready? Ooh. Okay, so I was on my list and I was working my way down and I chose to rewrite what was there using a trig identity. I had to make my own trig identity, but you know, it worked. However, what if I had decided that the effort of making my own trig identity was too much effort, and so I skipped the rewriting it, went to substitution, and I thought, no, substitution is not going to work because neither of these is the derivative of the other thing, and so that doesn't seem likely, and I need a sign there or something. And so I went to integration by parts next, which is specifically designed for things that are multiplied together. So I could use integration by parts to do this. It should work. And I wanted to do it for you here because I think it's nice to see how this works. And since we know what the answer is supposed to work out to, actually that's going to scratch that. You'll see what happens. So, okay. Integration by parts is about two things multiplied together. Traditionally they're called U and V. That usually freaks me out, but what would you prefer? U and V, F and G? Pick something else entirely? Sorry? F and G, okay. The first person who is brave enough to speak gives me the answer. This isn't finished yet. Okay. That's what integration by parts looks like. You have two things multiplied together inside an integral, and when you've finished, you get two pieces. Those are the parts that are being referred to. So you get something without an integral sign and something with an integral still, and we're going to have to do that integral. So one of the key parts to realise about all of these all of these techniques of integration is that they never do the integral for you. They always turn your integral into another integral that you hopefully know how to do. So what I did before is, rewriting this. It didn't do the integral for me. It just made a new integral that I knew how to do. And substitution doesn't do the integral for you. It just makes a new integral that you hopefully know how to do. So I'm hoping that when I get to this stage, the integral will be an integral that I know how to do. Okay. So I need to choose one of these to differentiate and the other one to integrate. That's how integration by parts works. One of them becomes integrated along the way and one of them becomes differentiated along the way. And the one that becomes integrated, I'm going to put a dash here to say that it's already the derivative of something and I'm going to have to integrate it to figure out what the answer is. Okay, so I get to choose which one has the dash. So it's either going to have a dash here and a dash here on the other one, or it's going to have a G dashed here and an F dashed here. It doesn't matter which one has the dash here as long as the other one has the dash here. So the decision that I usually make is to decide which one's going to disappear if I integrate it, like in the sense of becoming a constant. That would be really nice. Or hopefully become easier. Neither of them. All right, so it doesn't seem to matter which one I pick. So let's make, yeah, whatever. All right, I'm going to do that. If I was doing this very carefully, I would have left space to tell the reader what F and G were. And I'm going to do it really small just here, but normally I'd actually leave a space, do that bit, and then start again. But I'm not going to do that. I'm just going to put it in a little box and write it small. So the F is cos of 10x, because that's what lines up here. And the G dashed is cos of 9x. The reason I write it at the bottom is because in my head integration is up and differentiation is down. And so I have to put them that way for my own purposes. So the derivative of f would be minus 10 of sine 10x. Yep. And the integral of cos is sine, and I'll have to divide by that 9. Beautiful. Okay. So f is cos of 10x. G is a ninth of sine of 9x. F dashed is minus 10 sine 10x. And G is a ninth of sine 9x. This is not looking nice. But that's okay. Never to be so minus minus, yep, okay, they cancel out. Well, I still can't do that. Let's do integration by parts again. Okay, so this is going to be easier if I just rewrite this bit and do a new integration by parts. Okay. Right, well, it looks like I get to choose whichever one I want. And since I chose it to be the G that had the dash first, I need to do it again or I'm just going to undo what I just did. So I don't want to undo it because then everything will cancel out and I'll just get 0 equals 0 and it's not going to be helpful. So I don't want to put the F, I don't want to be the F dash here because I'm just going to undo it. So I'm going to go forwards. Right, okay. Let's see what we've got. Okay.
Is it meant to be for the second part, ft minus integral of f dash g?
Oh yes, thank you, well done. They have to be opposite way round, right? This one has to have the dash and then the other one, yes, well done. Beautiful. Moral of that tale is don't do your exam with other people. No, do your exam so we're in a place where someone can tell you whether you're wrong. I don't think that's productive advice, I'm sorry. The closer we get to exams, the crazier I'm going to get with the sorts of things I say. Just be aware of that. Okay. So we're going to do the derivative of sine 10x, well the 10 on 9 is still going to be there, the sine will become a cos, and I'm going to have to multiply by that 10, and the integral of sine is minus cos, and I'll have to divide by that 9. Okay, it's looking good. So the f was 10 on 9 sine 10x. The g is minus a ninth of cos 9x. The f dashed is 100 on 9 cos 10x. And the g is still minus a ninth of cos 9x. Which is interesting because that's where I started. We're not quite though, the numbers are different. I just want to see if I can, just let me simplify this a bit. 10x cos 9x plus okay, so that's where I've got to. So just a second. This thing here was that bit there. Okay, so let's just see what we get. So just a second. We started with this. And we ended up with a ninth of cos 10x sine 9x. And then we got minus a tenth over 81 of sine 10x cos 9x. And then we got 100 over 81 of cos 10x cos 9x. Nothing up my sleeves. If I put this over there, then there'll only be one of them. Ooh. So, all right. So I'm going to have one of these minus 100 over 81 of them. This is not the simplest way of doing this. But I really wanted to do this trick. Okay? If I put this over there, then I'll have to subtract. Now what's 100, or 81 over 81 minus 100 over 81 would be minus 19 over 81, I think. Yep, okay. Right. I don't feel like writing all this out. Can I skip that? I'm just going to do this here, and that's minus 19 over 81, right? And I'm going to have to divide by that to make it disappear. So this is really minus 19 over 81, there. And then I'm going to have to divide by the minus 19 and times by the 81. So let's see. When I times by the 81... that's going to become a 9 on the top. That's going to become a minus 10. And then that's times by the 81, and then I divide by the minus 19. Sorry. Right. There you go. Oh crap, there's no integral over here, so I need a plus c. Yay. Okay, so this is not the same answer that we had before, you will notice. So look at this, not the same. However, there is some fabulous trig identity that will turn this into that. I would say a similar one than the one we made earlier with the double angle formula, with the angle addition formula thing. What will often happen when you use Wolfram alpha is that you will use one method and it will use another one. Wolfram Alpha will sometimes, I don't know what its methodologies are for choosing, sometimes it'll use fabulous, usually it'll use fabulous trig identity to do your thing. That, you know, and you'll get an answer that looks very, very different from yours. But I would recommend graphing, if you were not in, you're using your Wolfram Alpha, you're not in your exam, graph them both and you'll see that they're the same, or at least just a constant apart from each other, which is what the plus C is about. All I wanted to do, the whole reason to do that was to say, yes, you could do it with integration by parts if you chose. So if you were in the exam or some other place where you were forced to do maths without any support, I don't know where else you would have to do that, but whatever. If you're in some place where you had to do maths without any support, and integration by parts was the only thing you thought of, then you could still do it. It would not be as easy. And it also brings the point there that it isn't as easy, actually. The reason why I put trig identities higher up the list is that in the situations where you use trig identities, it's easier to use them than any other method. And so I put them higher up the list of things to try. Okay. No. Okay. Oh, yes. My next fairly randomly chosen integral is this one. That is A shine. The exam that this is in calls it arc shine, but that's wrong to call it arc shine because shine doesn't use arc lengths. Shine uses areas, and so it's just A. So the integral of A shine x. If you see arc shine, translate it and say, oh, it's not really an arc, but I'll believe it. Okay, so A shine x dx. Aha, yeah, let's use that. Okay, just do it. Yeah, I don't know what the integral of that is, so I can't do that. Rewrite it. Not the worst plan, because I know that shine is written with e to the x in it, so it should be technically possible to rewrite arc anti-shine as an ln of something. But ln with crap inside it is not fun to integrate, so I don't want to do that either. There's nothing to substitute. Well, integration by parts is the next thing on the list. And there's a trick with integration by parts you can do where you sort of write it as 1 times that thing, and the 1 is your f and that thing is your g. So as long as I knew how to differentiate that, I might have a hope of integrating it using integration by parts. Do I know how to integrate arc anti-shine? Well, it can't be that different from arc sine. So if I could figure out how to differentiate A shine by using the same mechanism that I figure out how to differentiate arc sine, then maybe I could do it. Sweet. All right. You will note that if you are asked to do this in an exam, they'll have set it up already, and in part A of this question would have asked you to find the derivative of anti-shine. Okay? But I just wanted to pretend that I thought of it myself. Okay. So this is our goal. Our idea is to do this. Our idea is to think, okay, the first thing I thought of for figuring out what to do would be to write this as 1 times like that, and then do integration by parts like this. And I don't know how to integrate this So it can't be the one with the dash, so it will have to be this way. To be fair, I don't yet know how to differentiate it either, but that seems easier. Okay, so that's what I'm going to need to do. So I'm going to have to do, just as a little aside, f dashed is 1, and g is anti-shine, and the integral of 1 is x. Just nice, I can do that. And this I'm going to have to find. All right. Well, I'm going to have to differentiate something. So the classic way of differentiating an inverse function, because that's what this is to use the derivative of the original function. So if I do shine on both sides of this, that'll cancel out the anti-shine. Like that. And then just, it's not necessary to do this, but it's easier for me to think about it. No. I'm going to do dx on dy. And I know that the derivative of shine is cosh. Beautiful. And then dy on dx, which is what I really wanted, will be 1 on cosh y. Great. Except, damn it, the dy on dx is supposed to be a function of x. So I need to somehow get rid of this y and put an x in it. And this is not going to be something that I'm going to be able to deal with in my integral, because I'm going to have to still integrate what I get at the end if it's got cosh of anti-shine of x. Because, so I'm going to have to figure out another way to write this. And hyperbolic trig identities to the rescue. Okay, because I know the question I asked myself is, I know that shine y can be written as x. So if this was a shine y, it would just be 1 over x. So I need to ask myself, how is cosh y and shine y related to each other? And when I ask how things are related to each other, that means there's an equation that they're both in. And that's exactly what a trig identity is. So I know a trig identity. It goes like this. Cosh of thing squared minus shine of thing squared is 1. The classic ordinary trig identity has a plus in this spot. Cos squared plus sine squared is 1. It's cosh squared minus shine squared is 1. Now be very careful, because shine squared minus cosh squared is minus 1. So you need to have them the right way round. In fact, you need them in alphabetical order. Cosh, shine. Isn't that nice? Okay, so you need them in alphabetical order. In fact, everything to do with cos and sine is in alphabetical order. See, sine is the cos is the adjacent side, A, and sine is the opposite side, O, A and O, in alphabetical order. Really good, isn't it? Okay. So, cosh squared minus shine squared is 1, and I know what shine is. Shine y is x, so I can sub that in. Now, you may be asking, why have I chosen the plus? Because when I square root things, it could be positive or negative, right? Cosh is always positive, so I don't have to worry about that. Cosh of anything can't be negative, and so I don't have to worry about that. So I could say the positive root, since cosh y is always positive. If you were doing this for sine, you would need to go back and go, aha, well, if you were doing arcsine, then the y would have to be between minus pi on 2 and plus pi on 2, and that conveniently is the place where cos is positive. So, yes. But for cosh, don't have to worry about it. Okay, so we're doing very well. Cosh y is now 1 plus x squared. So just a second, dy on dx was 1 over cosh y, and so now it's 1 over root 1 plus x squared, because that's what cosh y is. Done! That was the, because y was anti-shine, and so it's the derivative of anti-shine that we've just found. And so in fact, so therefore, my g dashed is actually this. All right, so what were we trying to do? Oh, okay, right, this, okay. So the integral of anti-shine was fg minus fg dashed, and the f was x, and the g was anti-shine. I keep writing the h first. And the f is still x, and the g dashed is 1 plus x squared. Cool. So now I have to do that integral. All right, well, that's okay. It's all good. Because I can just pretend that this is the first integral I've seen. I can ignore everything else I've done and imagine what's happening. Ooh, it does weird things to the light, doesn't it? Imagining what's happening here. So, let me think. Well, can I just do it? No. Could I rewrite it? Yeah, that root's pretty bad. Suppose I could always write a root as like no. If it was on the top, then I might have a hope of doing 1 plus x squared divided by the root. No. Okay, so rewriting the substitution, well actually, this bit down here, the derivative of that is like 2x, which is nearly that. Yes, substitution is going to work. Okay, so we're going to go that u is root 1 plus x squared, and then the derivative of that is 2x, and du is 2x dx. Now let's see, I've got the dx and the x, I don't have the 2, so I might just move that out of the way. Okay, so my x dx, this bit just here, I've got that, x dx is a half of du. I've got the 1 plus x squared, that's u. There's nothing else left over, no x's, other x's I have to deal with, so good, I can do that. Oh damn it, I left my dx off up here. Don't want to leave your dx's off, it doesn't make any sense without that. Okay, so let's see. My x dx became a half of du. My 1 is still a 1, and that's a u. All right, so I've used substitution to turn this into yet another integral that I need to do. So here we go. Can I just do it? No. I could rewrite it though, because that u is that root u is a power of u. I can do that. Yes, now it's a power, I can just do it. Now the half will still be there because it's multiplied on. I'll put the power up by 1, which will go up to from minus a half to plus a half, and I'll divide by the new power, which is dividing by a half, so that's the same as timesing by 2. And u was actually 1 plus x squared. And power of a half is really a root, isn't it? Okay. Done. Ta-da. So you can imagine why your lecturers think this is such an awesome exam question. Because I used 3 different techniques of integration in one question. That's very efficient from an examiner's point of view. So I used integration by parts, and integration by substitution, and rewriting it as a power, which most people don't think is a proper integration technique, but I think it is. And not only that, you also had to do the derivatives of inverses things. So, like, yeah! Okay. You'll notice a couple of things about the way I wrote that. Maybe you won't, but I'll point them out. Every time I started a new page, I wrote what the thing was that I was calculating at the top. That's good maths writing. You should never start a page with an equal sign unless it's really obvious that nothing happened in between the previous page and the following page. It's just good for, makes it easier for the person reading it to know what's happening. And happy markers who find it easy to mark, people who find it easy to read your work are more generous. And also, from your own perspective, when you're writing things for yourself, you want to be able to follow it in the future when future you is studying this. And finally, you should always practice writing things exactly how you would like them to be. Never say it'll be okay in the exam. You will always do, under stress, the thing that you practiced. So if you practice writing it badly, you will write it badly in the exam. You must always practice doing it exactly how you want it to appear in the exam, even if it takes longer. The classic example of this, which if you've watched any other revision seminars I've probably said before, is that when they teach you how to use an EpiPen in your first aid training, you've got a fake EpiPen and you practice ramming it into your partner's leg. They used to get you to ram it into your own leg in training. What would happen is that when people were in a real first aid situation, they'd have someone in anaphylactic shock and they'd pull out their EpiPen and ram it into their own leg. Because under stress, you will do what you practiced. So you must practice the thing that you need to do. Okay, there you go. Moving on. Okay, I need a good integration by... Really? Okay. Wow. I need... one thing I was supposed to talk about is some of the... I hesitate to call them tricks. Tricks are a bad idea. But some of the strategies that you might use for creating reduction formulas. So, does anyone have some reduction formula things that they felt that it was a bit, I don't know what to do in the middle? It could be all possible reduction formulas. That's fine if you feel that way. But I don't know if there are any in particular that were a bit bamboozling, or if you've seen the solutions already and you're going, well, how did they decide to do that? Does anyone have any of those? And if not, I can try and find them myself. All right. Thing you did in the last assignment? Yeah. Yes. That one had like a root in it, didn't it? Okay. I can't remember what it was though. However, I could make one. I'm going to try one. So I'm going to do this example, and the hope is that you will see some things that might be useful along the way. Now I know that you were all wondering when you did integration by partial fractions, and you went, sure, I can put an ax plus b on the top of this and on the squared and whatever. What would I do if I actually got to the end of that? I mean, it doesn't really matter that they'll never ask me one of those questions because it just takes forever in the exam. I want to know. That's how you all felt. And so now we're going to do it. Okay, we're going to figure out what we would do in this situation. If it was no cubed there, I could just do it. I could do the arctan. Okay, arctan is the integral of that without the 3. But with the cubed or a squared, it's not so nice. So let us attempt to create a reduction formula for this as our way of figuring out how to do this. So, all right. So we could, well, the classic reduction formula move is to use integration by parts. I suppose I could do the classic 1 times trick. It's not a bad plan. This is not... Well, what do we reckon? I could try and do this by parts by splitting it into a 1 over x squared plus 1 and then another bit. And I know how to integrate the 1 over x squared plus 1 because it's arctan when I integrate it, and I could differentiate the other bit. But I have this horrible feeling I'm going to get this arctan floating around everywhere, and I'm not going to be able to make it go away. And when I do partial fractions, not partial fractions, just a second, reduction formulas, I really want to make it exactly equal to that. And if I've got something with x's in it that I'm not going to be able to make go away, then I'm not going to be able to do it. So I don't think that's the best plan. I reckon what I'm going to do is I'm going to do this, because that looks nicer. And I'm going to do this. And I'm going to use integration by parts. Because usually you use integration by parts. You don't have to. Some of them work by substitution. But this one, let's see how we go. Okay, that's going to be my f and my g. And I don't know how to integrate this one, so it can't have the dash, so I'll have to do it that way. So let's see. My f dashed is 1, and when I integrate f1 I get an x. And my g is x squared plus 1 to the minus n. So my g dashed will be minus n x squared plus 1 to the minus n minus 1 times the derivative of the inside, which is 2x. Might as well simplify it now while I'm at it. Minus 2n. Not particularly simplified, but, you know, slightly. And in fact, I'm going to write that as a minus n plus 1, because I like there to be an n plus 1. Well, actually, I'd really prefer it to be a minus 1, but I'll deal with that later. Okay. Cool. And so, what's my in? It's f, which is x, times g, which is my x squared plus 1 to the minus n, minus the integral of f, which is x, times g dashed, okay, right? All right. So they will be like that. The 2n I could move out the way because I don't really want that there. The the x times the x is an x squared. All right. So my goal is for this to look exactly like what I started with, except with a different power than it had before. Hopefully a smaller power, but well, we'll deal with that. So this is the same as what we had before, but with a different power. But we've got this x squared. I guess x squared is not all that different from x squared plus 1. Maybe we could do this. Like, make it like that. I could just make it x squared plus 1. I mean, I can't just make it x squared plus 1. If I'm going to add a 1 inside this bracket, I'm going to have to take a 1, or it's going to change what the answer is. But that's a thing I could do. And well, I suppose the only other thing I could normally do is just expand it out. Expanding brackets is almost never a bad plan if there's nothing else to do. Unless it's on the denominator of a fraction, and then don't. But even then, if there's nothing else to do, go for it. So this x squared plus 1 times this. So it was minus n plus 1, and then we add a 1. Okay, I'm just going to write it down just a second. Minus n plus 1 plus 1. Plus 1 to the minus n plus 1. Okay. That, I can, look, they're both the same as what we started with. They've just got the original but with a different power. We can deal with that. That I can deal with. So what do we get? We can separate this integral into two pieces. Now, minus n plus 1 is the same as minus n minus 1 and then plus 1. So that's a minus n. Okay. Well, at least I've done what I'm supposed to do when I'm doing integration by doing reduction formulas. I'm supposed to produce what I started with, but possibly with a different n. And I have that. This is exactly what I started with. It's got the same n. And this is exactly what I started. It's got an n plus 1. I would have preferred it to be smaller n, but, I'm just going to take what I've got. So in is x lots of x squared plus 1 minus n plus 2n lots of in minus in plus 1. That's what I have at the moment. Because this is the same as the beginning, so that's in. It's the same as the beginning, but with an n plus 1 instead of an n. Well, I've got in's, 2 of them, so I have a feeling I should just move them together. Maybe I'll just expand this out. And I guess if I put this over here, I'd have 1 minus 2n of them. So it's not really a reduction formula, it's like an escalation formula. Like, my n got bigger. Oh, damn it. But I guess if I want my n to get smaller, I could go from n plus 1 down to n. That would tell me how the n to get, that would make the n smaller. Right, before I do that, which is a very specialised trick, notice that this thing is nearly done. If this was an n minus 1, then that's what happened in the assignment. Okay? But you now know an even cooler trick, which is to rewrite it with the biggest n, which is the biggest value of n, which in our case is n plus 1. I'm just going to switch this around a bit. I'm going to do this instead. I'm going to subtract this from both of these to produce this, and I'm going to add this to both to put it over there. And that tells me how to make things smaller. If I start at n plus 1, it gets me down to n. It's not really what I want. But I suppose if this is supposed to work for every n, right? Can't I just sub n minus 1 in instead of n? Like if this works for this n, it should work when n is n minus 1 as well. So I should be able to just bump everything down a step, which is just so much fun. Okay, so sub in n minus 1 for n. That's a fabulous trick. It's one of my favourite tricks. So that's unlikely to be something that happens in the exam, though I would be most gratified if your lecturer did put something like this in and you all knew how to do it. That would make me very happy. Yes. Right, so three major things happen there that are strategies that you can use when you're stuck doing reduction formulas. One of them was here. I rewrote what I had here so that it looked more like the other part. Okay, the bit that was annoying, that was attached, I got the bit that I want, and then this other little annoying bit. I rewrote that annoying bit so it looked like the part that I really wanted. And then I expanded it out. And then there was this move where I had two copies of something and I could bring them together so that it was a little easier to deal with. And then there was this very specialised move where I just subbed in the next number down because my reduction formula went in the wrong direction, which is probably not going to happen all that often, but you never know. Okay, so now I have a reduction formula. I would need to use it to do my integral. I'm going to do another, depending on how much time we have. Yep, I'm going to do another one of these in a minute, and the classic sine and cos version one, so that you can see that move, a couple of those moves again as well. But for the moment I want to finish this off. I was trying to figure out the third one. We wanted I3 because it was with a 3 in that spot. So let's just think about how this reduction formula works. It will start at I3 and it will get me down to I2 because it's n minus 1. And then I could use the formula again to go from I2 down to I1. And then I could use the formula again to get down from I1 to I0. I don't think that's productive. We know what it is when it's 1. I don't think I0 is going to make any sense. I1. I1 is arctan, and we know that one. So let's do that. We need to get down to I1. So we want I3. My reduction formula is going to be able to turn that into I2, and then that's going to turn that into I1, and I1 is the one that I knew how to do. So you know that very first thing that I did right at the beginning when I covered up the power and said, I would know what to do if it wasn't a cube. That's where I need to get to. Find out what the power needs to be for you to know what the answer is. I know what the answer is when it comes down to have no power there, and not having a power is the same as having a 1 in that spot. So that's where I want to get to. And why did I do all of that? It's important to think about this in advance so that you don't just do it forever, because it doesn't work at some point. And secondly, it's much easier to start from the bottom. At least it is for me. I'm much less likely to lose minus signs when I do that. So let's see. I1 which is arctan. It's okay to leave all your plus c's out of these for the moment because you don't really care what they are with the plus c. You only want an integral, so this is fine. You just put your plus c in at the end. If you not doing a plus c now will mean that you're less likely to do it when it's important, then do it all the time. So why not? Okay. I2, according to this formula, is 1 over 2 times 2 minus 1, which is 1, times x squared plus 1 minus 2 minus 1, which is 1, plus 2 times 2 minus 1, which is 1, over 2 times 2 minus 1, which is 1, I, 2 minus 1, which is 1. X squared plus 1. That's 1 over 2. And I1 is arctan. Beautiful. And according to the formula, have I got enough room to do it all? Yes. I3 is 1 over 2 times 3 minus 1, which is 2, x squared plus 1 to the power of minus 3 minus 1, which is 2, plus 2 times 3 minus 1, which is 2, over minus 1 over 2 times. That's I2. That's how my formula works. So what have we got? 4 minus 2. That's 3 over 4. So I need, I2 is all this. I need 3/4 of I2. So we've got 3/4 of this would be 3/8 of x squared plus 1 to the minus 1, and 3/4 of this would be 3/8 of arctan x. And I3 was the thing I wanted, and so that's the answer. There you go. That's making and using a reduction formula with a very fancy trick, actually. All right. Let's do another one. On a brand new page. I'll just leave that there. Just to make it interesting, might stick a 2 in there. All right. Let us attempt to do this one, which I shall call IN. Let's pick a number. No, whatever. Yeah, whatever. I could put a 2 in this spot, right? But I wouldn't use a reduction formula if this was a 2. I'd use a trig identity, because there's a trig identity that turns cos squared into 1 and cos 2. So I'm not going to do that, because no one would use a reduction formula for that. I'm going to put a 4 in this spot. All right. Now, to be fair, you can make a trig identity that does cos 2x to the 4, but and plus this is probably the sort of a question where they go, well, make a reduction formula, because they've specifically asked you to. Okay. No, not with a 4, with an n. Okay. All right. Well, I need to somehow do something that will turn this into an integral that has cos 2x in it to the power of something, but the power is hopefully smaller. But if it's bigger, then we'll be okay, because we know how to do that too.
Do substitution first.
Substitution? So you could call this u.
Yeah.
Okay. Let's give it a go. Du on dx would be the cos differentiates to give a sine, and there'd be a 2 as well. Well, I'm going to need a sine 2x. Which I don't have. Can I put it there? I suppose I could multiply by sine 2x and then divide by sine 2x, but that's just not going to help. Oh, it's such a good idea. We might have to come back to this anyway. So, well, we'll just hold that in reserve, but I might rub it out for now. Well, normally you do these things by integration by parts. I could do the 1 times trick, but if I did that, then I'd get an x when I integrate that 1, and everything would have an x attached to it, and I wouldn't be able to make that x go away, because I couldn't move it out the way. And I couldn't use that trick that we used last time. When we did that last time, the x combined with an x squared, and I could go, oh, it's not very far from x squared plus 1, but I'm never going to be able to turn an x into a cos 2x. So no. So I might have to create the 2 parts by separating that into 2 pieces. Like that. Oh, if I did it with a... No, that's not going to work. Okay. All right. Okay. So, well, this I didn't know how to integrate because that was the whole point. So it's not going to be able to have the dash, so this one. Okay. So let's see. So the f dashed was cos 2x, and I know how to integrate that. Cos would go up to sine, and I'd have to divide by that too. Cool. And the g was, damn it, I should have given myself more room. The g was cos 2x to the n minus 1. So the g dashed will be n minus 1 cos 2x to the n minus 1, 2 times, now what's the derivative of cos would be minus sine. Oh crap, but because of the 2 I'm going to have to do that. Alright, there we go. That's not fun, but you know, it's not worst thing. Sine 2x. Yeah, that really isn't any better, but that's okay. At least the minus isn't in the middle, which has always freaked me out because I'll lose them if they're in the middle. Okay, so my in is now f, which was a half of sine 2x, g, which was cos of 2x to the n minus 1, minus the integral of f, which was a half of sine 2x, times g dashed, which was minus 2, ooh, nice, 2x times cos of, wow, this is bad. You really need to put your page landscape to do reduction formulas. Okay, so what's going on here? I reckon I can do something that half and that 2 are going to multiply out to give 1 and disappear, so that's nice. That minus and that minus will become a plus. The 2, there's 2 of those, they can become a squared, okay. Cos of 2x plus sine of 2x squared cos of 2x to the n minus 2. Okay, that's not too bad. Oh, we lost the n minus 1, sorry guys. You may have noticed that it's not the worst habit to be into to just check if everything that was on the previous line has appeared in the next line, which is how I knew that the n minus 1 was missing. I was working my way along and just making sure that everything ended up somewhere. Okay, right. Well, let's just compare. I don't really care about constants. This is what I started with, but with an n minus 2 instead of an n, which is nice, at least it's lower. And we've got this. So last time when we had an extra bit that we didn't like, we rewrote it so that it was more similar to the thing that we were hoping for. So I need to rewrite that sine 2x squared as something that's about a cos 2x instead. Well, there's a formula for that. Sine squared is 1 minus cos squared. Beautiful. And that I can expand out. Not a plus. Equals. So I'll copy this bit. So let's see. I can expand it out inside this integral if I want. And maybe I will, because I feel like I'm going to lose one of those minus signs if I don't. So the n minus 1 and the cos 2x to the n minus 2 times the 1 is this. In fact, I could think of it like the integral, right? This and this times the 1. And no, it's not going to fit there. And this and this. Whoop, sorry guys. I can do that. So this and this times the cos 2x squared, when you do powers, the powers add and I get this. All right. So this is exactly what we started with except for the n minus 1. So that's n minus 2. N minus 1 there is going to have to end up being at the front of the integral, and the n minus 2 is here. Oh, damn it. Sorry, guys. Right. So these two go together. And in fact, just so that it's easier to read what belongs with what, I'm going to write them in the same positions. So those two things are the same, those two things are the same, and those two things are the same. Now if I move this over here, it's trick number 2, right? We already used trick number 1, which was I see a bit that I don't like attached to the bit that I do like. I need to rewrite this so it looks more like that, which is what I did. And then I expanded it out, and now I have 2 of these things. well, technically not 2. I have 1 here and n minus 1 here. So when I move this over, I'm going to get 1 plus n minus 1. Which is n. 1 plus n minus 1 is n. So that's n. So I'll divide by the n and I'll be done.
Why is it n minus 1 over 2n on that last bit?
Oh, crap, you're right. Thank you. Yes, we're just dividing by n. Nice. Okay. So I think the only difference between this and your ordinary cos reduction formula is this 2 just here. Well, and obviously the 2's inside, but you know. So which one did I want? I wanted I4, didn't I? Well, okay, this is my reduction formula. So we want I4, which will go down to, because it's n minus 2, that'll go down to I2. And I2 would be cos squared, which I could conceivably do with the trig identity, but it seems like a lot of work when I've done all of this. And I0 yeah, it makes sense to do x to the 0 on when it's not on the bottom of a fraction. So I can do that. So I0 we can do. There's a thing in here to the 0. And anything to the 0 is 1. Now you're thinking probably, but David, what if the cos 2x was 0? Is 0 to the power of 0 equal to 1? Most of the time it wants to be 1, so we're going to let it. Okay. Sometimes it wants to be 2 or infinity, but today, in the terms of integrals, it almost always wants to be 1, so we're going to leave it at that. Okay, and so this is just x. Okay, I2, according to the formula that we just calculated, is 1 over 2 times 2 sine 2x cos 2x to the 2 minus 1 plus 2 minus 1 on 2 I0 cos 2x plus a half of, and the I0 is x, and I4 according to the formula is 1 over 2 times 4 sine 2x cos 2x to the 4 minus 1, which is 3, plus 4 minus 1, which is 3 over 4i2. So this bit is an eighth of sine 2x cos 2x to the 3. And this bit, we need 3/4 of that bit. So 3/4 times 1/4 would be 3/16 of sine 2x cos 2x, and 3/4 times 1/2 would be 3/8. Ta-da! Wow. Reduction formulas take ages. To be fair, they take slower when you're not explaining to someone else what you're doing. Faster. If you're not simultaneously dealing with, people muttering that you're doing it wrong and having to explain what you're doing at every moment, then it's a bit faster. Yeah. Most exams don't ask you to both make reduction formulas and use reduction formulas at the same time because there's not enough time to do both. However, I'm not going to stand by that because 2 years ago they did it. So, yeah, it's important to know how to do both. But just be aware that there's a lot of times when they'll try and do part of it for you. So keep a close eye on them doing that sort of thing, where they've told you what the reduction formula is and then asked you to use it, or gone halfway and asked you to finish. Yeah, important to realise that. Well, thank you everyone. I wish you clear thinking and a good night's sleep and calm nerves in your exam. Maths Learning Centre is open until the end of the exams, and we're also open during the break, so if God forbid you need to do a replacement exam, you can still come and talk to us about that too. I believe your lecturer's consulting time is right now if you want to go and talk to him about calculus. It's my duty to say that sort of thing. Thank you. Okay, so you're saying when you're doing trig substitution,
Yeah.
tan/sec thing.
Yeah, or a sine or cosine.
Yep. It's to do with where the minuses and variables are. So if I saw something that was like something like that.
Yeah.
The only trig identity I know off the top of my head is the fundamental one that involves squares.
Yep.
So, see, this has got a variable, and that's a variable, and that's a plain number. And so I'm going to arrange it to look as much like this as I can. So if I move this around, it will just be variable equals number minus variable, which is not what this looks like.
Oh, so that's when you have to divide it by cos to get signing.
So if I get this, I get... And now it's variable number plus variable equals variable.
Yeah. Yeah, that's confused. Yeah, that makes a lot of sense. Though.
Yeah. Yeah, it's to do with where the minuses are. So you need to arrange to have a trig identity with the variables and the numbers and the pluses and minuses in the same spot. That's how I make the decision.
Yep.
From this point, I'd be multiplying everything by 4 to make that match.
Yep. And then you can take that into the bracket. But you can just take 4
And then this needs to be 2x squared.
So you can just take the 4 into that bracket.
No.
2 tan x.
Well, I've got 4 tan u squared is 2x squared. So I actually get 2 tan u is root 2x.
Oh, okay, yeah.
And so I actually divide everything by root 2 and I get this. That's my substitution.
Oh, okay. Yeah.
Because I need this to match that.
Yeah.
Yeah. And so now I can do my dx on du and start subbing things in for the rest of the crap that's there, which I have neatly just ignored where it is. But yeah, that decision-making process is, there is one. It's not just do more and experience. Yeah, anyway. So yeah, for me it's, I compare what I've got to the shape that's there and I think, well, if I move that, will I get the plus that I need? No, I won't. So the only way I'm going to get the plus that I need is to divide by something. Yeah.
Cool, thank you.
I've got a question. So for the exams, will they provide like a simple formula sheet of like trig identities?
Traditionally, no.
Okay, fair enough.
In the past, if you needed to use the cos of alpha plus beta, they'd usually give that one to you in the question that you need it for. But I don't know what they're doing this year. That's the sort of question you need to ask your current lecturer to see what they've done. But usually, no, they don't give you trig identities. You're going to have to just know them.
Thank you.
They're big on the memory thing. Hey.
For example, I missed the first one that you were doing last week, and where to find it. Just
Yep. Yes, I've spent all weekend trying to get that online. Just let me